Yes, let's go to work together. So this is what we are going to discuss together later on in this lecture. So the idea is that we want to learn how to deal with this kind of question in a systematic and possibly easy way. So we will gradually build to be able to answer this question. So this will be probably something we'll do toward the end. Before starting, just let me know if you have any question about our previous lectures, and also if you hear me well, if you can read what I write and the usual thing. So the topic of today, while you think, is going to be, let's see. So here is what we want to do today. We want to do exercises on LAG. I think is 9 and 10. So we want to speak about rank of matrices and linear system of equations, Roche-Capelli theorem, and the like. Okay, so everything seems to be working good. So let's start with a few warming up exercises. So coming from the exercise sheets. So just to warm up a little bit. So let's have a look at this one. So A, 1, 0, 1, B, 1. A and B are real parameters. And then there is a question. So for what values of A and B in R is the matrix, let's give it a name, A, row reduced. So these kind of questions, as we saw in the suggested problem, deal with matrices which have inside them not only numbers, but also parameters, which usually range in some set. For example, the real numbers could be the complex number, could be any other set that we are interested in. And then we want to study properties of these matrices. So for example, now we ask a mid question with respect to the rank computation we saw before, and we're going to study together. And mid question is, well, is this matrix row reduced? For what values of A and B? Okay, so the idea is that for each value, possible values of A and B, you have to give an answer. So usually when you give an answer to this question, it will say, it will look something like for A equal this or that, or for A different from this or that. Similarly for B, these hold, or these does not hold, okay? So for example, for this kind of question, we want to study row reduce. So we have our properties M1, M2, M3 that we want to focus on. And this means that, well, we need to go and look for markers. So let's start the mark identification process. I see a marker here of row 2, and then there is a question about the rank of, the markers for row 1. Because you see, saying that this one is a marker requires A to be different from 0, while if A is 0, then this is not a marker, but this one is going to be. So we have to make some case analysis, just starting here. So we want to say that if A is different from 0, then I look at the matrix and I see two markers here. And then we have all the rest, 1, B, 0, 1. Okay, so since I have two markers in the first row, I have to proceed and do something, apply elementary row operations, for example, to get rid of some of the markers. So one thing I can do is to say, well, I will change row 2 into row 2 minus A row 1. Note that this is possible no matter what the value of A is, right? Can be 0 or not, is not a problem, but we know it's not 0. So what we do here is to have this situation. Well, sorry, this is going to be 1 over A. So we're going to have 0 here, B minus 1 over A here, and 1 at this level. Okay, and then I look at the markers. I have a marker here, and then I have to look in this position to see what happens to this number here. So now I have a condition. If B is different from 1 over A, then here is the values of our, what I want to say is that this matrix here, sorry, is now row reduced. Is row reduced. Okay, so what is the situation? Well, the situation is that if A is different from 0, then this matrix here is not row reduced. So A is not row reduced because there are 2 markers in the first column. And if I want to do row reduce it, I can follow this process. I find a new condition here, and then I find a row reduced form of matrix A. If I want to keep looking for a row reduced form of matrix A, I have also to say that if B is equal 1 over A, then the matrix I have here is not row reduced. So this one is row reduced. But now this one is not. So the one here is not row reduced, or it is. What do you think? Is it row reduced or it is not row reduced? It is, because if you have a 0 here, so this gentleman here is equal 0, then I have the 2 markers like this. So it is actually row reduced, right? So, well, let's do like this. So I have the markers. And so we can say that, yes, it is row reduced. So for A different from 0, the original matrix is not row reduced. And we found that we can row reduce to this form when A is not 0 and B is not 1 over A, or to this form when A is not 0 and B is equal 1 over A. If A is 0, because now we have to also look for that case, if A is 0, then here is what we have: 0, 1, 1B, 0, 1. Look at this matrix, we find immediately the markers, and we say, well, it is not row reduced, right? Because there is no property M2. So it is not row reduced. Remember, the markers have to go from left to right when you go top to bottom. And if I want to row reduce it, I have just simply to make a row swap. Now it is row reduced. So it was easier now, and there is no condition on B when A is 0. So it is row reduced. Okay. So the answer is then that our original matrix is never row reduced for any value of A and B, but we can row reduce it, okay? Just by following these precise operations. And if you look at the conclusion, so just make a side question, what can we say about the rank of matrix A? Do you have any idea about the rank of this matrix? Okay, so let's see some of the question. Pranav Tripathi says, is it that any matrix can be row reduced by applying hero? Yes, it can, but it needs original form. It is not row reduced. Okay. Then Sara Bordone. Yes, by in this step here, by switching row 1 and row 2, so an elementary operation of type 3, we row reduce it. Yes, exactly. And then there are some suggestions about the rank. Well, the rank of this matrix is actually 2. 2 for all values of A and B in R. Why? Well, because it is written here. If A is 0, then A is row equivalent to this matrix here. So copy paste, and let's make it like this. So it is row reduce, the one we wrote now, and it has 2 markers. So it has rank 2, 2 non-zero row in a row reduced form. And then if A is 0, sorry, if A is not 0, either what happens? A is row equivalent to the first form we found, this one here, in which we have markers in these positions. So either it is row equivalent to this one with markers A, which is not 0, and this one, which we assume is not 0, or A is row equivalent to a matrix like this, A10, 0, 0, 1. And again, there are 2 non-zero row in the row reduced form, and so the rank is always 2. No matter what happens to A and B, the rank of this matrix is always equal to, okay? No question about that. It is always equal number 2. Okay. Any question about this? It is probably okay, right? Okay. If you have any question, you can ask while I scroll a little bit up. And then we see one other kind of exercise, if we want. So say we want to row reduce this matrix here, 0, 1, 1, minus 1, 0, 1, and minus 1, 0. First, you have to ask yourself, is this matrix row reduced or not, right? So, because if it is, well, we stop. Is A row reduced? What do you think? It is not. And why is that the case? Well, because I see these markers and they do not satisfy our properties, not M1, not M2, okay? And then the next step is, well, I'd like to apply elementary row operations to make it row reduced. This is always possible, we know. So since it is not row reduced, what I do now, I apply arrows to obtain B row reduced, A and B row equivalent. So let's see what you can do to find this matrix B. Okay, just a couple of minutes so you see what you get. If you want to share your answer, if it is nice to write down. And then, since I see some answer already showing up, we can also ask ourselves, what is the rank of matrix A? Right, so Gabriele Taricco, what do you think is the rank of this matrix? Well, you have the answer right there, right? Just to revise the definition, what did you need to do? We need to count the non-zero rows of a row-reduced form. So to answer to this question, we simply count non-zero rows of B, which is, what is B? Well, it is a row-reduced matrix, row equivalent to A. Okay, so now let's see together how we can perform this task here. Very briefly, what do we need to do? Well, we need to follow our procedure. So Gaussian elimination. And what we do to perform Gaussian elimination here? Well, we do the following. We want to, well, get rid of the extra markers. And usually it is a good idea to have markers on the top. So let's see. It's probably a good idea here to move the first row in position 3. So I'll do that. And to have the third row in position 1. This is just to make our life easier. It's not necessary, but it is probably a good starting point to say I exchange row 1 and row 3. And then what we do? Well, we want to use the marker in top position to clean up all the rest. Okay, so I keep the third row is nice as it is. Now we want to get rid of this marker, so subtraction. So I will say I change row 2 into row 2 minus row 1. So minus 1 plus 1 is 0, 0 minus minus 1 is 1, and then I have 1. So now the marker situation is like this, almost there, and you see that the two last rows are equal. So in the last step, I will get something like this: minus 1, 0, 0, 1, 1, 0, 0, 0. And also we can get rid of this minus if I want, just simply by multiplying by 1. Okay, and this means that the answer with the minus 1 is correct, no problem about that. The answer with the ones is correct, no problem about that. And they share the fact that there are two non-zero rows in this row reduced form. So our conclusion is that the rank of matrix A is equal number 2. Okay, now I have a question for you. Since A is 3 by 3, I can ask myself, what is the determinant of A? So can you tell me what is the determinant of A? It is 0. Yes. This determinant is equal to 0. And I will ask you, why is it 0? Well, of course, one option is computed, and we get it 0. Someone says, well, 2 rows are identical. Well, I don't see 2 identical rows here. Some assume thing, right? There are not 2 identical rows. It is true at this level, so the rank of this matrix is 0. Okay, but we are speaking about, sorry, the determinant of this matrix is 0, not the rank. The rank is 2. But we are speaking about the rank of determinant, sorry, of the original matrix A. So why is it 0? Giancarlo Dones-Rivera, again, you are computing the rank of, sorry, the determinant of this matrix here, not the rank determinant of the original matrix A. Someone says the diagonal is 0, so the rank is 0, but that's not true, right? Konstantinos Eleftheriou is not true. What can we do? And just make a note. Well, the determinant of this matrix here is far from being 0, right? Even if it is 0 on the diagonal. So don't make that silly mistake, okay? So someone asked, well, maybe there is something when matrices are row equivalent about the determinant. Well, let me help you a little bit. So let's make a note. The matrix A is equal to its transpose with a -1 in front of it. Do you agree? So let's take the original matrix A. Here it is. Let's carry it downstairs. You see, this is a skew-symmetric matrix. So A is skew-symmetric. So what happens about skew-symmetric matrices? Well, we need the fact that the determinant of A is equal to the determinant of A transpose. This is always true. This is a fact about the determinant of a matrix and the determinant of its transpose. We mentioned that already, and we'll see a proof when we finish our part about determinants. And can you use this fact to deduce that the determinant of A is 0? Can you make this implication clear? Using the fact that the matrix is skew-symmetric. Yes, in some sense, what happens is coming from what is written here. So take this as a kind of preview. The determinant of A is equal to the determinant of minus A transpose. And this is equal to minus the determinant. Well, let's do like this. It is -1 power 3 determinant of A transpose. Again, this is something that you can check for the 3×3 determinant, this equality here, but it will be definitely clearer when we finish our part about determinants. And so you get that the determinant of A is minus the determinant of A. And so it must be 0, okay? But there is also another interpretation that I believe it is the one you can fully understand without any further ingredient. So since A is a matrix, row equivalent to this one, when you look at the system AX equals 0, this is equivalent to the system BX equals 0, right? Because the two matrices are row equivalent. Now, using Rouchet-Capelli theorem, what can you tell me about these system of equations? How many solutions do you see? So it is a 3x3 system. And what is the rank of B? We said it is 2. And so there exists exactly infinite to the 1 solutions. So let me ask you, does AX equals 0 has infinite to the 1 solutions? And now let me ask you, can A be invertible? What do you think? Can A be invertible? Of course not, right? No, it cannot be. Because if it is invertible, if it were invertible, then we would have exactly 1 solution. And since it is a 3x3 matrix, if the determinant is different from 0, you can find the inverse, right? So hence, the determinant of A must be equal to 0. So what is the idea which we have here? The idea is that if you have A squared, n times n, and the rank of A is less than n, then the determinant of A is equal to 0. Why? Well, because the system AX equals 0 has infinitely many solutions. How many solutions? Well, it has infinite to the n minus r solutions by Rouchet-Capelli theorem, right? So when you find a matrix square having the rank which is not as big as it should be, sorry, could be, then the matrix is singular. It has determinant 0, okay? Okay, let me know if you agree with this last note, which is one of the first times in which we relate the rank and the determinant. Then I like to answer to Lireza Nafarjabit, who said something about the rank of a matrix and the determinant of a matrix for matrices which are row equivalent. Actually, I didn't mention any. Oh, the theorem you say here. So the theorem here is Rouchet-Capelli theorem. You know, we have two propositions, Rouchet-Capelli theorem 1 and 2. Sorry, Rouchet-Capelli 1 and Rouchet-Capelli 2. And then the Rochet-Capelli theorem is the combination of both of them, saying that the number of solutions is possible to describe, to count how many solutions there are using this notation, but for sure there is more than one, and so the matrix cannot be invertible. Even if it is square, cannot be invertible, okay? Okay, and then let's make a final note. If you have matrices which are row equivalent, it is not true that they have the same determinant. And you can see this in a very simple example. Look at the identity matrix, which is row equivalent to this one, right? But the determinant of the identity matrix is equal number 1, while the determinant of this matrix here you can compute is number -1. Okay, so it's not true in general that row equivalent matrices have the same determinant. They have the same rank, but they don't have the same determinant. What is true, and this is again a preview, we'll see, what is true is that if A is row equivalent to B, then the determinant of A is 0, if and only if the determinant of B is 0. So row equivalent matrices have the property of having a determinant of 1 equals 0, even if the other one is 0. So what is true is that row equivalent matrices are both invertible or both non-invertible, but the value of the determinant can be different. Okay, it's not the same number. Okay, good. Now let's move a little bit farther on. And let's see again something about rank computation. Okay, so let's say we want to compute the rank. For any A in R of the following matrices: 1, 0, 1, 0, A, 0, 1, 0, 1. Okay? Sophia Karnaut says that the determinant is 0 if and only if the rank is different from n. Yeah. So what we wrote here is one implication of what Sophia is suggesting. The rank is less than n. Sorry, is here. Where is it? Yes, here. If the rank is less than n, then the determinant is 0. And what happens is that the converse is also true. If the determinant is 0, then the rank cannot be n. Exactly. So we'll see that it is an if and only if. Yeah. Okay, so we have an answer here. Giancarlos Herrera says, if A is equal to 0, the rank is 1. Otherwise, the rank is 2 for any A. Okay, how do we answer this kind of question? The answer you propose is correct. You go and look for markers. The matrix is not row reduced, so I cannot read the rank, so I need to row reduce it. Well, sorry. This one is a marker only if A is different from 0. Otherwise, the second row is 0. So applying an elementary row operation, I can clearly go here because row 1 and row 3 are equal. So I just make the easiest thing, subtracting them, changing row 3. into row 3 minus row 1. Okay, and then here we have a marker here, 1, and then if A is not 0, I have another marker. So this is in the case A different from 0, while in the case A equals 0, we get this situation here. So in this case, we see that the rank of A is 2. And in this case, we see that the rank of A is 1, as you suggested. Okay? And also, let's make a note. What can you tell me about the determinant of A? Depending on A and on the parameter A. What is the determinant of this matrix? Is it 0 for all values of A or only for some values of A? What do you think? For all. Yes, this is 0 for all values of A. And the reason is that the rank is never 3. So this means that the linear system of equation AX equals 0 will always have infinite to the 1 or infinite to the 2 solutions. And so the matrix is never invertible. The determinant is always 0. Yep. This is exactly how we can perform this kind of computations. Yep. That's exactly what we want to do. Let's just take a look to another of these exercises with parameters. So we practice that once more. So now we have a new matrix. Here it is, 1, 0, A, 0, 1, 0, A, 0, 1. And then we ask the same question. So let me copy it so it will be easier if you ever need to read this again. So we want to compute the rank for any A in R. So what can you tell me about the rank of this matrix when A varies in R? Okay, so we have some suggestion here, but let's make some remark, some initial remark. So A is 3 by 3. So the rank of A can only be rank of A is either equals 0, 1, 2, or 3, right? Cannot be anything else. So what do you think? Can we have rank 0? Can we have rank 0 for matrix A? This can sound silly, but okay. So for example, Nikola Stankovic, why do you say the rank cannot be 0? Can you give me an explanation? Why is the rank never 0? For example, yep, R2 is always non-zero. So the idea is that the rank is 0. Just remember, if and only if A is the 0 matrix. And this cannot be, right? Because there are numbers here which always are non-zero. Okay, then what about rank 1? What do you think? Can we have rank 1? Sophia Karnauk says R2 is linearly independent on the other 2 rows for any A. Well, what Sophia is saying is that I have always these 2 markers, right? So having rank 1 happens if and only if all rows are, well, let's say like this, multiple of one row. Okay, and this is not the case because the first two rows are linearly independent. They have two markers, right? So the rank cannot be 1. So let me say this cannot happen. These cannot happen. So the only possible values of the rank are 2 and 3. Yep. So this is a kind of thought we can always make. Okay. And then you see something has to do with the value of A, because if it is non-zero, then it is a marker. So what we notice that if A is 0, then the matrix take this shape here, 1, 0, 0, 0, 1, 0, 0, 0, 1, and so the rank is 3. The rank of A is equal 3 because it is just the identity. Okay. If A is different from 0, then A is is row equivalent to the following matrix: 1, 0, A, 0, 1, 0, and then I multiply by A the first row and I subtract to the third. Is third minus A first. So I get 0, then I get minus A, and then I get 1, right? And so you have a marker here, marker there, and then what we do? We do one further reduction step to get 1, 0, A, 0, 1, 0. Then I multiply by A, the second row, and I sum. So I do row 3 into row 3 plus A, row 2. Okay, and so what is the conclusion here? Thus, the rank of A is 3. So our conclusion is that the rank of A, hence, the rank of A is equal 3 for all values of the parameter A. Okay? Rank of A is equal 3 for all values of the parameter A. And this means that, what about the determinant? This means that the determinant of A is different from 0 for all A in R. So this means that if you go back and you compute the determinant of the matrix here, well, Konstantinos Eleftheriou says that there is a mistake here, because I wrote row 3 minus A row 1. Thank you for noticing this. Thank you. So we have to take these two things back because we need to compute again, right? Thank you. Because you see, the number you get here is the number 1 minus A square, because we change row 3 in row 3 minus row 1. So there is this number 1 minus A square. Thank you. So we have to amend my mistake also here. Now I multiply by A and I sum, and what we get is 1 minus A square. Okay, sorry. Thank you for noticing this. So here are the markers. Yep, thank you. And so what happens? If the last one, this number here, is 0, well, then I get rank 2. But if it is not 0, I get rank 3. So what is the conclusion? If 1 minus A square equals 0, then the rank of 8 is 2. rank of A is equal to, if 1 minus A squared is different from 0, then the rank of A is equal 3. So you see there is only one situation in which the rank is not 3, which is this one, A equal plus minus 1. Thank you for letting me know this. And this is actually pretty clear, because if A is 1, then the matrix has the shape 1, 0, 1, 0, 1, 0, 1, 0, 1. So you see that there are two rows which are equal. So when you do elementary row operation, for sure, you clean up one of it. And if A is equal minus 1, well, the shape is like this. And you see that these rows are not equal, but they are proportional. So minus 1, the first, is equal to the third, and so I can clean it up again. And these are the only cases. So about the determinant, if you go and compute it, what you will see is that the determinant of A is equal to 0 if and only if A squared is equal 1. Otherwise, it is not 0. Okay, thanks for the remark. These are the computations. And you see, when the rank is not 3, the determinant is vanishing, and we have linear relations among the rows, because the rows are not linearly independent, right? So let's make a note. If I have my matrix M times N, if the rank of A is less than M, then the rows of A are not linearly independent. Why? Well, because by performing elementary row operations, I will get a 0. So one of the rows will disappear. Okay? Perfect. Jorge Balmaceda says, wouldn't that mean for A equal 1 also? Well, exactly. The determinant is 0 in both cases. So this is matrix A, this is matrix A, and the determinant is 0 in both situations. Because there is a linear combination of the rows which give you 0, or rows which are multiple of each other. If you compute it, use the formula, recursive formula, and you will see that the rank is 0. Okay. Okay, let's go a little farther on. And now let's speak about some application of Rouchet-Capelli theorem. Yes, the last note, Erfan Far, basically says this. If the rank is less than M, it means that my original matrix A, which has M rows, is row equivalent to a matrix having at least a 0 row. I don't know what is on the top, but there is a 0 row. Having a 0 row means that, for example, row M is a linear combination of the previous rows. So this is telling me that Rm belongs to the linear span of R1, Rm minus 1. Thus, the set of all the rows, all of them, is not linearly independent, right? This is exactly what the note means. And this is what you get when you have the rank, which is not equal, for example, to the number of rows. So just as an example, if we get a matrix like this, so 1, 2, 3, 4, 5, 6, and I ask you, are the rows linearly independent? What would you say? Yes or no? Are they linearly independent or not? So are the rows linearly independent or not? Yes, the answer is no. And why is that the case? Because the matrix is 3 times 2. So there are 3 rows. But since I have these 2, this means that the rank, call it A, whatever it is always less or equal than 2. Right? It's always less or equal than 2. Sayed Mostafa Sayeri, no, the rank is not 1. Try reducing, you will see it's not 1. And to see it's not 1, you simply note that the rows are not proportional. It's not true that second row is a multiple of the first row, right? So just have a look to that and you will see why the answer is that the rank is not 1, and actually it is 2. Okay, the rank of this matrix is 2. So it's a computation that you can easily perform. Okay, now let's say about linear system of equations, just one easy one, say this one. And x plus y equal 3. So we want to do the following thing. 1, answer the question, are there solutions? Yes or no. Second, how many? And third, compute. So the first 2 questions is what you answer using the Rouchet-Capelli results, 1 and 2. Right? This is what you need to say if solution exists or not and how many. Computing the solution is part of the process of row reduction. But let's see what you get here. Are there solutions? Yes or no? How many? Infinite to the whatever. And then you can compute the solution and see what you get. So let's see how far you can go. Okay, so we have some suggestions here. And Jean Herrera made probably the right approach. So what you have to do is to look for the matrix A and the matrix AB, so the augmented matrix, and you have to compute the rank of A, the rank of the augmented matrix, and then you have to compare them. And we said that it is enough to compute the rank of the augmented matrix because these will give the complete answer. So let's do that. So I write down the augmented matrix. So it is 0, 1, 1, then 1, 0, 1, and then it is 1, 0, 0. Then I put the known terms here. I know that the matrix is not row reduced, so I cannot read the rank just by looking. So I have to do something, say, smarter if I want to compute the rank. So say that we proceed by making a row swap. So I just put the last row and the first, I swap them. So here we go. So let's get rid of the extra stuff we don't need. So I swapped row 1 and row 3. So now we are in a better shape for the rank computation. And then I use the first row to clean up the second row. So this is what I want to do. So let's do this. Okay, so I just do the following. I take row 2 minus row 1. Okay, let's clean this up. So I get 1 minus 1 is 0, 1 minus 0 is 1, 0 minus 0 is 0, 3 minus 2 is 1. So here is what we get. And then let's make the final step. Of this operation. So let's see what we get here. And then we clean up row 3 about that. Someone says there is a mistake with the second row, and you are correct. Sorry, there is a 1 here. Thank you. So I just need to replace the second row, which is now the first, right? Thank you. So I put it here. And so when I make the subtraction, I get a -1 here. Thank you. Thanks. So now we copy the first row. I don't need to touch it anymore. The second row, which is now correct. And now I don't need to touch it anymore either. And then we can subtract row 3 as row 3 minus row 2. So we get 0, 1 minus 1 is 0, 1 minus 1 is 2, 1 minus 1 is 0. Okay, and then what we do at this point, well, now the matrix is row reduced, and you see all the markers are in the first part. So this means that the rank of A is equal to the rank of AB, and this is equal to 3. So there exist solutions. How many solutions do we have? Well, it depends on the Ruchet-Capelli theorem telling us, and there exist infinite to the number of unknowns minus rank solutions. So this means that there exists a unique solution. What is this number counting? Is the number of free parameters. And here there are no free parameters because, as you see, x, y, and z can be all computed. So the idea is that this equation will produce z. And this equation will produce y, because I know the value of z. And the first equation will produce x. So I get all solutions in this back substitution process, right? So what do we get is that z must be 0, and then y minus z is equal 1. Y minus z is equal 1, and x plus z is equal to. So I get that z is 0. I get that y is 0. So sorry, there is a problem here. That the problem is, here it is. So we took this matrix and then we make this subtraction. Yes, this is what we got. We got to this level. And then we get that this is not a 0. This is a 1 because it comes from this equation here, right? So y is equal 1. And then x is equal to. Okay, so here is what we get. The unique solution is x equal 2, y equal 1, and z equals 0. Samuele Clavero, yes, this is exactly what it should be and what it is. Yeah, thank you. I realized that. And so we produce the solution 210, which is the unique solution. Also note, if you don't have questions, let's make a quick note. So let's make a quick note. The note is that A is a 3 by 3 matrix having rank 3. So you can find the inverse of A. So in other terms, you can solve the system by multiplying by the inverse or using Cramer's rule to compute the values of the unknowns. Okay, those are options you can follow if you want to compute the solutions in a slightly different way. But the result, of course, is going to be the same. Nothing is going to change. Okay, any question about this process? Okay. So let's do a similar analysis here. Now, we want to solve a linear system of equations adding parameters. For example, we want to study the system for A and B in R. So here is the system, for example, x plus ay equal 1, x plus by equal 2. What does it mean to study the system? Well, it means to answer to the previous question for all A and B in R. Consider the question, there exists solution. So are there solutions? How many solutions? Are there? And finally, compute the solutions when they exist. Okay, so this is what you want to do when you have a system with parameters. This is the question we consider. Keep in mind that these can come easily from applications. Maybe, you have your mathematical model, you have your problem, you manage to produce linear equations. This happens, for example, in physics when you have static equilibrium, right? And then you want to find the solutions. But maybe your system, your physical configuration is not exactly one, but it depends on parameters. You can change the configuration by varying A and B. So you want to find a solution to study the system depending on A and B. Okay, So let's see how you can do this. And again, one tool of doing this is to use the augmented matrix and rank computation. So let's see what you find, say a couple of minutes, and then we do this together. Okay, so we have a complete suggested solution by Jean Herrera. So the idea is, well, to write down the augmented matrix, and these I do. Then I go look for the markers. That's the usual process. And I row reduce. So by row reducing, I 1A1, then 1 minus 1 is 0, B minus A, and 2 minus 1, which is 1. So what do we see? We see that we always have a marker here, and then depending on B and A, I can have a marker here or not. If I don't have a marker here, so if B is equal A, then what happens? Well, the rank of A is 1, which is less of the rank of AB, which is 2. And no solution exists. Right? So if B is equal A, no solution exists. And if B is different from A, then what happens? Well, it happens that this gentleman here, B minus A, is a marker. So it happens that the rank of A is equal to the rank of AB, which is equal number 2. And you have a unique solution because you have infinite to the 2 minus 2 solutions, right? And in this case, it is pretty easy to see what the solutions are, because you have equation x plus a y equal 1. And this equation, the second one, tells you what is y, 1 over b minus a. Then you substitute here, and you compute the value of x. Okay, so this is the situation for this exercise. Okay, if you don't have questions about this one, I just go on the top for a second and I go back. And I like to say something about, okay, so it is the last page we wrote. Here is the situation. And I just want to say something about this one. And what you need to do here is the usual row reduction process, okay? So this is what will help you to find the solution. So we want to study the rank. What I'll do is to write here the computation, so you can have a look after. But I suggest that now, after we computed a little bit of these rank of matrices with rank, and we studied a little bit of system, I suggest that you go back, use what we learned today to do this, and then you will find the solution in the PDF notes that I will upload after the lectures, okay? So try, see what you get, and then you compare with what we do together. Okay, do you have any further question about these topics? Okay. Okay, so Salvatore Lagrasta has this question. Well, the idea is that, so let's follow this approach. So A is square, right? So you look at the system AX equal 0. Okay, and you know that there always exists a solution that is X equals 0. Okay, if A is invertible, X equals 0 is the only solution. Because I can multiply by A minus 1. So you see, if this system has a unique solution, when the matrix is square, you find that it is invertible, okay? Vice versa, if it is invertible, a unique solution exists. This is what we want to establish. So what we want to establish is that AX equals 0, so there exists a unique solution if and only if there exists the inverse. This part here, this should be clear. It's just the definition, okay? It's just a definition. Going backward, it requires the rank, because by Rushet-Capelli theorem, existence of a unique solution means that the rank of A is equal n. And from these, and using the matrix, you remember A and IN, you can find the inverse of A. And so A is invertible. So this is another way of seeing this, okay? Okay, well, Alireza Nafajabadi, the idea is that we will speak quite a lot about linear span in the future. So you will have occasion to see it again and again. I suggest you play with 2D and 3D geometry to make it clear what it is. Also think about what you already learned about ODE, you know, the ordinary differential equations. You can go have a look and see that the solution space is given by linear span. So there will be time to overcome this problem, but you can start having a look into these recursive just by comparing. Okay, so have a nice day and see you again next week, right? Bye.